All right, let's spark some curiosity today and dive deep into electrostatics. Got a physics textbook chapter here and pretty interesting stuff about electric charges and fields.
It really is fascinating, how we went from like basic observations about amber to, well, all the theories we have now.
Yeah, it's amazing how it all started with that piece of amber.
Right, 600 BC, Thales of Miletus. Notice that thing about amber attracting stuff
And bam, the word electricity was born.
from electron, the Greek word for amber.
Yeah.
It's pretty wild.
So what's the most mind-blowing thing you've seen in this chapter? Anything that really stood out?
I gotta say, it's Coulomb back in the 1700s figuring out his law, the force between charges. But get this, without knowing the charge of an electron.
Wait, hold on. He didn't know about electrons? How do you even measure the force then?
Torsion balance, super sensitive, picked up even the tiniest forces. He messed around with the distance between charged objects like really carefully, and boom, figured out the relationship. Charge, distance, force, all there.
Wow, that's pretty ingenious.
Oh, absolutely.
So he nailed down that force is proportional to, what was it, the product of the charges, and inversely proportional to the square of the distance.
Bingo. And that equation, F equals K, times
Yeah.
Q1 times Q2, all over R squared. Still the foundation of electrostatics.
That's a pretty big deal.
It-
Thinking about it, how does that compare to gravity?
Oh man, huge difference. Like take a proton and electron. The electric force between them, quadrillion times stronger than gravity. That's 2.4 followed by 39 zeros.
Okay, so electric force, strong, got it. But why don't we see stuff flying around, sticking to each other all the time?
Because most stuff is neutral. Equal amounts of positive and negative charges. They cancel each other out.
So it's like a tie.
Yeah, kinda, like a cosmic tug of war. But things get interesting when we mess with that balance, like rubbing a balloon on your hair.
Ah, that's when the electrons start jumping ship, right?
Right on. Friction makes those electrons move. One material to another. You get an imbalance, then bam, electrostatic forces show up.
And the balloon sticks to the wall. Classic.
It's all about those two types of charge, positive and negative.
Yeah, and they don't exactly get along, do they?
Nope. Like charges, they repel. They're like, get out of here. Opposites attract. They're all come closer. Basic principle governs how they behave.
So like two positive charges, they're going to push each other away.
Exactly. Repulsion city,
Yeah.
but a positive and a negative. Instant attraction.
Okay, I'm starting to see the pattern here, but how did they figure all this out? The charges, I mean.
Well, early researchers, they were clever. Simple experiments. Glass rods, silk cloth, rub them together, see how they attract or repel.
That's how they cracked the code.
Pretty much.
Yeah.
Led to tools, too, to
Don't it?
detect and measure these charges. The gold leaf electroscope, for example.
Ah, yeah, I remember those. Little box with like gold leaves. Bring a charged object near, they freak out.
They do. They're repelling each other because they got the same charge. Pretty cool visual. Really shows how charges act.
So much to learn from these tiny little charges, huh? Speaking of conductors and insulators, what's the difference?
It's all about how charges move or don't move. Conductor, it's like a party, charges roam free. Insulator, charges stuck in place.
Okay, so metals, good conductors. Electrons in them are loosey-goosey, ready to move.
That's it. Free electrons flowing through, conducting electricity like champs.
But plastic, rubber, those guys, electrons are more, stuck.
Stuck. Insulators, they resist the flow of charge. That's why we use metal wires to conduct and, well, plastic to insulate them.
Makes sense. The right tool for the job, based on how the charges move. Okay, so we've got the charges, conductors, insulators. Now what about the electric field?
Ah, yes, the electric field. Invisible force field surrounds every charge, messing with the space around it.
Okay, charges detract, repel, we get that. But how does this invisible field work?
Imagine a charged object, a sphere, let's say positive charge. Now picture a tiny, tiny positive charge just wandering into the space around that sphere.
Okay, I'm picturing it. Tiny charge approaching the big charged sphere.
As it gets closer, it feels the sphere's influence. Force pushing it away or maybe pinning it closer. Depends on the charge.
So the electric field's like a map, telling you the force at different points.
Exactly. Tells you the direction, the strength. Stronger field, stronger force.
Got it. But how do we see this field? It's invisible, right?
We use electric field lines. It's more of a concept, a way to visualize it.
Oh, right. The diagrams, lines coming out of charges, like arrows pointing the way.
That's it. They show us the structure of the field, start at positive charges and at negative. How close they are, that's the strength.
So lots of lines packed together, strong field.
Strong field. And they never cross. That'd be like two directions at once. Doesn't make sense.
Right, chaos. So these lines, even though they're imaginary, they help us map the field.
Like a secret code for the language of electrostatics.
I like that. Speaking of codes, what's electric flux?
Electric flux. Think of water flowing through a net. Amount going through depends on how fast the water is moving, size of the net, the angle it's at.
So is electric flux like the amount of electric field going through a surface?
You got it. How much field is flowing through an area.
So more lines, more flux.
Exactly. And the angle of the surface matters too, just like the net and the water.
Okay, I'm seeing the connection. But why is this flux thing important?
Because it leads to Gauss's law.
Yeah.
And that, well, that's a game changer.
Gauss's law sounds kind of intimidating. What's the deal with that?
It's a shortcut for figuring out electric fields when things are symmetrical. It says the total flux through a closed surface, any surface, is proportional to the charge inside.
So no matter the shape, we can find the charge inside using this law.
Yep. It's like X-ray vision for charge.
That's awesome. But you mentioned symmetry. Why is that important?
Symmetry makes things easier. We can pick surfaces where the field is either perpendicular or parallel. Makes the math way simpler. We'll see examples later, but for now, just trust me, Gauss's law is elegant.
All right, I'm willing to trust you on that one. But before we go any further, let's take a quick pause. Lots to digest here.
A break is definitely needed. Back in a bit to keep exploring electrostatics, so stay tuned.
Welcome back to our deep dive. Gauss's law, that was pretty cool. Using it to calculate the field of that infinite wire.
Yeah, definitely shows you the power of symmetry, picking the right surface and all that.
It's amazing how much easier it makes things. But what about more complex shapes, not just wires that go on forever? Like what about a charged sphere?
You're thinking about the thin spherical shell, right? Uniformly charged. Another great example for Gauss's law. Some interesting stuff pops up there.
So picture a hollow ball, charge spread out evenly on the surface. How do we even start figuring out the field for that?
Same as before. Pick a Gaussian surface that, takes advantage of the symmetry.
Yeah.
And for a sphere, another sphere is the way to go. Concentric with the charged one.
Okay, so like a sphere that either fits inside the charged one or surrounds it completely.
Exactly. And because it's all symmetrical, the electric field, same magnitude everywhere on the surface, pointing either directly out or directly in.
So the field lines are like spokes on a wheel.
That's the idea.
Huh.
Makes calculating the flux through that surface pretty easy. Just the field strength times the area of the sphere.
Okay, got the flux. And Gauss's law connects that to the charge inside. What's the next step?
Now it gets interesting. Let's say our Gaussian surface is outside the charged shell.
So our sphere is bigger, totally encloses the charged one.
Right. The charge inside is just the total charge on the shell.
All right, we got the charge, we can calculate the flux. So Gauss's law gives us the electric field outside the shell, right?
And get this, the result is surprisingly simple. The field outside that shell, it's exactly the same as if all the charge was concentrated at the center. Just like a point charge.
Oh, seriously, it's like the shell is pretending to be a point charge.
That's what Gauss's law tells us. Symmetry simplifying things again.
That's wild. What about the field inside the shell then?
That's where things get even weirder. Imagine the Gaussian surface is now inside the charged shell.
Okay, a smaller sphere hanging out inside the charged one.
How much charge is inside that smaller sphere?
Well, none, right. It's all on the shell's surface.
Exactly. No charge. Gauss's law says no flux.
So the field inside is zero.
Zero. Vanishes completely. Might seem counterintuitive, but think about it. Any point inside, surrounded by charges on all sides, canceling each other out.
Like being in the middle of an electrostatic hurricane, but calm in the eye of the storm?
Perfect analogy. And there's the field being zero inside, it's been proven, experiments back it up.
It's amazing how these laws can lead to such unexpected results.
Speaking of which, remember that early atom model we talked about? Positive nucleus, cloud of negative charge around it.
Yeah, you mentioned using Gauss's law to figure out the field inside.
Right. Simple model, but still useful. So, tiny nucleus in the center, then this spherical cloud of negative charge, uniform density, out to a certain radius.
Okay, got the picture. And the total negative charge equals the positive charge of the nucleus, right? Electrically neutral.
Exactly. How do we find the field at different points within this atom? Gauss's law to the rescue again.
We can use the spherical symmetry like we did with the shell.
Right. Spherical Gaussian surface.
Yeah.
Centered on the nucleus.
Yeah.
Two cases. Gaussian surface inside the cloud and outside the cloud.
Okay, let's start inside. Gaussian sphere smaller than the atom within the cloud.
Flux through that surface, same idea. Field strength times area.
And Gauss's law says that's equal to the charge inside, divided by permittivity of free space.
But here's the catch. The charge isn't just the nucleus anymore. Got to include the negative charge within the Gaussian sphere, too.
So we need to figure out how much of that cloud is packed into that smaller sphere.
Use the charge density and the volume of the Gaussian sphere.
So we know the charge, the flux, Gauss's law gives us the field strength inside the cloud. What do we get?
The field inside is proportional to the distance from the nucleus.
So the further you go from the nucleus, the stronger the field gets, at least while you're still inside the cloud.
Yep. Now, outside the cloud, things are different.
Because the whole atom is neutral, right? So the total charge enclosed is zero.
Zero charge, Gauss's law says zero flux.
So the field outside this atom model is zero, just like inside the charged shell.
You got it. This model shows how, even at the tiny scale of atoms, charge distribution and Gauss's law can explain how electric fields behave.
From infinite wires to atoms, it's amazing how it all connects. Like, we're uncovering some hidden language of the universe.
Speaking of hidden, this atom model also shows us something called shielding.
Shielding? What's that?
It's like a conductor blocking an electric field. Like the charged shell, remember. Field inside is zero because the charges on the shell cancel out any external fields.
So the shell's like a protective barrier.
Exactly. And in the atom, the cloud of negative charge, it shields the nucleus's field from reaching outside the atom.
So even though the nucleus is positive, its field doesn't affect things further away.
It's like the negative charge forms a cocoon around the nucleus.
Shielding, that sounds useful. Any real-world examples?
Oh, tons. Coaxial cables, for one, for cable TV, internet.
Yeah, I've got like a million of them behind my TV. What do they have to do with shielding?
They have a central conductor and then a shield around it, usually metal. Protects the signal from interference, like stray radio waves or electrical noise.
Like a bodyguard for the signal.
That's a good way to put it. And then there's the Faraday cage, the ultimate shield.
Oh yeah, Faraday cages, they block all electromagnetic fields, right?
Right. It's basically a hollow conductor. The way charges arrange themselves on the surface, any external fields get canceled out inside.
So you could be in one during a thunderstorm, lightning all around, and be totally fine.
In theory, yes. As long as it's built right and grounded, the lightning's electric field wouldn't get in.
That's incredible. A personal force field against electric fields.
Pretty much. Shows you the power of electrostatics, how we can use it.
Shielding, that's my new favorite thing. It's awesome how these ideas, they have real-world uses.
And there's one more thing that affects how charges behave in different materials. Permittivity.
Permittivity. Sounds complicated.
It's about how much a material allows charges to interact. Remember that constant K in Coulomb's law. Depends on the medium.
Yeah, the one that changes depending on where the charges are.
Right. That constant, it's inversely proportional to the permittivity.
So higher permittivity means weaker force between the charges, like the material is getting in the way.
You got it. It reduces the strength of the electric force.
So why is it different for different materials? Is it like resistance to electric fields?
It's more about how the molecules in the material react to the field. Apply a field, the molecules can polarize, means they get a little separation of charge, like tiny dipoles.
Like they're aligning themselves with the field.
Exactly. And those dipoles, they create their own field that opposes the applied field. It's like the material's pushing back.
So materials with easily polarized molecules, they have higher permittivity because they can create a stronger opposing field.
Right. Like water, for example.
Water. Seriously. But water's everywhere. What makes it special?
Water molecules, they're polar. They have a permanent separation of charge, like a built-in dipole moment.
So they're already ready to align with a field, creating that opposing field and reducing the overall field strength.
Exactly. And this high permittivity of water, it has some big effects. It's one reason why water is such a good solvent.
Wait, how does that work?
Think about dissolving salt in water. The salt breaks up into positive and negative ions.
And they're attracted to each other because of the opposite charges.
Right. But the water molecules, with their high permittivity, they surround the ions, reduce the attraction between them.
So they're like little peacemakers, calming things down.
Exactly. They act like shields. The ions can separate and dissolve.
Never thought about it like that. Permittivity, pretty important then, for chemical reactions and stuff.
Super important. Affects how charges behave everywhere, from atoms to, well, materials and solutions.
It's amazing how everything's connected in science.
That's the beauty of it, right? Different ideas all linked by these basic principles.
Speaking of links, remember how we talked about the electric force being way stronger than gravity?
Yeah, the proton and electron thing, quadrillions of times stronger. Mind-blowing.
I know. But then, why is gravity the boss on a large scale? Shaping galaxies and all that?
Good question. It's about how the forces work on different scales. Electric force, yeah, it's strong, but things are mostly neutral. So the forces cancel each other out,
So they're fighting it out on a tiny level, but on a bigger scale, it's a tie.
basically. But gravity, it's always attractive. More mass, more gravity. So it wins on the cosmic scale.
Makes sense. So electrostatics might not be shaping galaxies, but it's still super important. Atoms, materials, technology, it's everywhere.
Absolutely. The more we learn about it, the more we see how amazing it is.
I feel like we've learned so much already, but there's got to be more, right?
Oh, definitely.
Mm.
Electrostatics is full of surprises. But for now, let's take a break, recharge a bit, back soon to wrap things up.
It's amazing how gravity takes over on a large scale, even though it's so much weaker than the electric force. It really makes you think.
It really does. But even though gravity might be shaping galaxies, electrostatics is still shaping our world, in all these little ways we don't even think about.
That's true. We've been talking about all these abstract ideas, but I'm curious about some real-world examples. Like, where do we actually see electrostatics in action?
Well, let's start with something super common, something you've probably experienced a million times. Static electricity.
Oh, yeah, that little zap you get when you touch a doorknob after walking on carpet.
Exactly. Or when you rub a balloon on your hair and it sticks to the wall. That's electrostatics, plain and simple.
So what's going on there at the atomic level when we create static electricity?
It's all about the electrons, those little guys. When you rub two different materials together, some of those electrons jump ship, from one material to the
So
other.
it's like an electron exchange program?
Yeah, kinda. The material that gains electrons becomes negative, and the one that loses them becomes positive.
And then, boom, opposite charges attract. The balloon sticks to the wall. It's all because of those sneaky electrons.
Exactly. And that zap you feel, that's the static electricity discharging. The potential difference between you and the doorknob gets too big, and those electrons, they jump the gap.
So it's like a mini lightning bolt right in my fingertips.
That's a great way to think about it. It just shows you how powerful those electrostatic sources can be, even on a small scale.
So static electricity is kind of cool, but I'm wondering about more practical uses. Is there anything else electrostatics is good for?
Oh, tons of stuff. Think about printers, for example. Laser printers, inkjet printers. They both use electrostatics to get the ink or toner onto the paper.
Really? I use my printer all the time. Never knew that. How does that work?
Well, with laser printers, you've got a laser beam that creates an electrostatic image on a drum. That image attracts toner particles, and then those particles get transferred to the paper.
So the electric field is actually guiding the toner.
Exactly. And in inkjet printers, it's similar. The tiny ink droplets get charged, and electric fields steer them to the right spot on the page.
That's amazing. I had no idea electrostatics was behind all that. What other everyday things use this stuff?
Well, let's see, air purifiers, for one. A lot of them use electrostatic filters to clean the air. Get rid of dust, pollen, all that
So
stuff.
it's like an invisible force field capturing those tiny particles.
Pretty much. The filter charges the particles, and then oppositely charged plates attract and hold on to them so they can't get back into the air.
That's pretty clever. An electrostatic trap.
It's a neat trick. And it's not just everyday gadgets. Electrostatics is super important in all sorts of scientific instruments, too.
Oh, I bet. Like what?
Well, take the mass spectrometer, for instance. It uses electric and magnetic fields to separate ions based on their mass-to-charge ratio.
So it's like a super precise scale for atoms and molecules.
Exactly. Helps scientists identify and study different substances. And it all starts with manipulating those charged particles using electric fields.
Electrostatics is like the unsung hero of the science world. What else is it used for?
Don't forget about electron microscopes. Those use beams of electrons focused by electric and magnetic fields to get these incredibly detailed images.
So you can actually see things at the atomic level.
That's the idea. Electron microscopes have revolutionized so many fields, from materials science to biology. We can see the tiniest structures thanks to electrostatics.
It's incredible how these principles, starting with a simple observation about amber, have led to all these amazing tools and technologies.
It's a great example of how scientific curiosity can lead to incredible breakthroughs.
Well, I think we can call our deep dive into electrostatics a success. We've
Okay.
covered a lot of ground: charges, fields, laws, dipoles, shielding, permittivity, and all the cool things electrostatics makes possible.
It's been quite a journey, from tiny atoms to the vastness of space, all linked by the fundamental principles of electrostatics.
So the next time you feel a static shock, or print a document, or even just breathe in clean air, Take a moment to appreciate the invisible world of electrostatics at play.
And never stop being curious. There's always more to discover in the world of science.
That's right. Thanks for joining us for this electrifying episode of The Deep Dive. We'll see you next time as we explore more of the fascinating mysteries of the universe.